Okay, imagine you're watching a perfectly balanced seesaw. It's just sitting there, not moving. Now, what do you think would happen if I suddenly dropped a heavy backpack onto the left side? Think about it for a second. That's exactly what Le Chatelier's principle helps us understand about chemical reactions. Here's the core idea, the single most important concept here. When you mess with a chemical system that's at equilibrium, maybe you add more of a reactant or remove some product, the system is going to react in a way that tries to undo what you just did. It's like that seesaw pushing back, trying to get balanced again. Before we dive deeper, we need to be crystal clear on what equilibrium means in chemistry. You might think it means there are equal amounts of everything, right? Nope, not quite. It means the forward reaction, things going from reactants to products, is happening at the exact same speed as the reverse reaction. So even though concentrations look constant, there's always activity. This is the equilibrium constant, K. It's a ratio that tells us how much product there is compared to reactant when the system is balanced. See how it's products over reactants? And those square brackets just mean concentration. Super important point. K stays the same for a given reaction at a constant temperature, no matter what concentrations you start with. That's key. So, Henri Le Chatelier basically formalized that seesaw idea. He said that if you poke an equilibrium, it's going to shift to fight back against your poke. Specifically for concentration changes, if you add more of something, a reactant or a product, the reaction shifts to use that something up, and if you take something away, it shifts to try and make more of it. It's all about minimizing the disturbance. Let's take a real-world reaction. Nitrogen plus hydrogen making ammonia. This one's super important in industry. At equilibrium, a value we call Q is exactly equal to K. Q is calculated just like K, but it can describe any moment in time, not just equilibrium. Now, watch what happens when we mess with it. Here's the expression for Q for our ammonia reaction. It looks just like K, right? The exponents come from the coefficients in the balanced equation. We compare Q to K to figure out which way the reaction needs to go to get back to balance. Okay, so you suddenly dump a bunch more N2 into our reaction. What happens to our Q value? Well, N2 is in the denominator, right? So increasing N2 makes the whole denominator bigger, which means Q gets smaller. Now Q is less than K. To get Q back up to K, we need to make the numerator bigger, which means making more products. So the reaction shifts to the right. You'll see more ammonia being formed. What if you remove some of the product, NH3? This time, the numerator of Q shrinks. Again, Q becomes less than K. The solution? Shift right. The system responds by making more NH3 to replace what you took out. Pretty cool how it tries to maintain that balance, isn't it? And the opposite. If you add more NH3, now the numerator of Q gets bigger, Q becomes greater than K. To bring Q back down to K, the system needs to decrease the products and increase the reactants. So, the reaction shifts to the left. It's breaking down some of that extra ammonia you just added. Quick check. Does that make sense? Here's a little flowchart to cement that in your mind. See how adding reactants always results in a shift, right? Making more product? And adding product leads to a shift left, making more reactant? This is the fundamental cycle. You disrupt it, and the system tries to restore K. All right, let's work through a full example. This is where it all comes together. We have hydrogen reacting with iodine to make hydrogen iodide. Here are the starting concentrations and the equilibrium constant K for this temperature. Now, what happens if we suddenly add more hydrogen? Let's break it down step by step. First, we calculate Q immediately after adding the extra H2, but before any reaction can occur to reestablish equilibrium. Remember, our new H2 concentration is 0.30 m, so we plug in the numbers. We get Q equals 8.0. So we have Q at 8.0 and our K value is 12.0. Since Q is less than K, to get back to K, Q needs to increase. This means the numerator needs to get bigger and the denominator needs to get smaller. That tells you the reaction is going to shift to the right, making more HI and consuming some of the H2 and I2. This matches our prediction from Le Chatelier's principle. Adding a reactant pulls the reaction forward. To find the new equilibrium concentrations, we use an ICE table, initial, change, equilibrium. Our initial values are what we calculated after adding the extra H2, but before the shift. The change row uses X based on the stoichiometry. For every X moles of H2 that react, X moles of I2 react, and 2X moles of HI are formed. See those coefficients? They're super important here. Now, we plug these equilibrium expressions back into our K equation and set it equal to 12.0. This is the part that might look a bit intimidating because it involves solving a quadratic equation. For this specific problem, if you crunch the numbers, you'd find that X is approximately 0.041 m. Don't worry too much about solving the quadratic right now. The setup is key. Now that we have X, we can calculate the final equilibrium concentrations. Just plug X back into the equilibrium row of our ICE table. Notice a couple of things here. The H2 concentration is lower than 0.30 mg, meaning some of the added H2 was used up, and the HI concentration is higher than 0.60 mg, confirming our rightward shift. This is exactly what Le Chatelier's principle predicted. All right, if you only remember 3 things from this whole lesson, let them be these. 1. Systems at equilibrium fight back against change. 2. Add reactants, shift right, add products, shift left. It's that simple. And 3. K, that equilibrium constant, is tough. It only changes if you change the temperature. Changing concentrations doesn't change K, it just makes the system adjust to get Q back to K.